This is Star Trackers and Celestial Navigation put together by Midterm Group 6. Alright, so when you're in space, how do you go about describing where you are or where other objects are around you? Here on Earth, we use things like mountains and rivers as reference points. But obviously, there's none of that in space. And to add to that, the Earth is of course constantly spinning on its own axis and orbiting around the Sun at the same time. So if everything is moving, what can we even use as our point of reference? What we need is called an inertial space, a reference frame that is constant and can be referenced anywhere in our solar system. And our solution is to use the stars dotting our night sky. Stars other than our Sun are incredible distances away from us, and therefore their relative movement is negligible. Stars are the best reference frame we can get, so we assume them to be stationary, and we use them as a basis for all other reference frames that we may need to use in space while exploring our solar system.
So overall, celestial navigation can be defined as finding one's way by observing the sun, moon, and stars. And this has been done for hundreds of years to navigate the oceans using things such as the North Star. So reference stars are extremely far away, so they can assume to be fixed and used as a relative point to determine any position or orientation. Constellations or specific stars are particularly helpful and are basically a landmark as a bridge or a large mountain in the distance. This strategy can be applied also to surface navigation, not only space navigation, helping rovers and other ground vehicles on the moon or uncharted territories like Mars. Star trackers, which are the device that performs the celestial navigation, track the necessary stars to calculate the orientation of a spacecraft. They're made up of cameras, complex electronics, and a software unit. They're pivotal for any spacecraft, such as satellites, that need to be particular on their orientation and control. They're often uniquely designed with an appropriate camera and specifications and software. It is widely desired that there's an open source star tracking software, although it has been difficult with designs being so specific to their hardware. Well, how do star trackers work? So the image is initially taken, while it also records the direction at which the picture was taken. This picture is then analyzed and cross-referenced by some database containing positions of stars already. Once matched within the database, the spacecraft's orientation and other sensors can determine exactly where the spacecraft is pointing. This data is then sent to the attitude control system, where any changes are made to correct the spacecraft's orientation. At the bottom of the slide is an actual flow chart, basically saying what I just went over visually.
Historically, celestial bodies have been used to track time and navigate through the universe. By using sundials and constellations, civilizations have been able to determine the time of day or night or the best seasons for agriculture. In addition to this, celestial bodies have been widely used for sea navigation. Records show that as early as 3000 BCE, stars have been used to navigate the seas. Widely known tools that have been known to aid in celestial navigation is the astrolabe and the sextant. In the images on the right, it shows examples of how these instruments were used by using the sun or the stars. As for tracking the stars, the enhanced eye of Galileo was used to make early observation of the stellar parallax, a star's apparent motion. As more accurate maps of the stars were needed for maritime navigation, the Paris Observatory and the Royal Greenwich Observatory were started to further astronomy and track the stars using the stellar parallax to provide precise maps of the skies.
Right, so for current uses for star trackers, they're mainly used in orbiting satellites for satellite attitude determination. So they're used in conjunction with reaction wheels and other devices to control the attitude of the spacecraft. And then also on deep space missions, what's pictured in the top right is Voyager 1, which was a deep space satellite that used star tracking. And with the recent technological advantages, these can be purchased off the shelf. So the bottom left image is Rocket Lab's star tracker that essentially you can buy off the shelf and use in conjunction with your satellite. They're also super important for spacefaring telescopes. So originally with Hubble and now with James Webb, star tracking is super important to get accurate pointing for imaging. Then it can also be used as a backup to GPS, even for aircraft. So these can even be used on like military UAVs. So if GPS is down or they're in a particularly like bad weather area, then star tracking can be used as a backup. And then for the future uses, currently in development is an open source model. So most star trackers are very expensive. So for CubeSat and other budget missions, an open source model would be super helpful. And then also hypersonic aircraft, as they go higher and faster, star tracking can be a useful alternative to GPS. And then also just developing accuracy and speed of these models to be able to use for more complicated missions in the future.
One of the most critical components of the star tracker is the algorithm used to convert the raw star image data into useful data about where the spacecraft is pointed or information about its attitude. Most of these algorithms follow the same general format of comparing the measured stars with known star locations from a catalog. One of the most common star catalogs was generated by the Hipparcos satellite launched by the European Space Agency in 1989. The newest version of the catalog can include more than 2.5 million stars. The geometric voting algorithm is a common algorithm used for larger spacecrafts that can fit star trackers with higher FOVs because it needs to capture more than 6 stars to be useful. The basic principle is for the algorithm to take votes on which stars that are measured correlate to which stars from the catalog. It does this by converting those measured stars into a matrix filled with ones and zeros, representing if stars were picked up or not in that location. At the end, it'll tally up all the votes for certain stars from the catalog and then make a decision on which stars it thinks those correlate to. Another type of algorithm is the angular separation algorithm, where the star tracker will make pairs of stars from the measured data and then calculate those angular separations and compare those separations to the star catalog. And it wants to try and make the absolute value of the differences from those stars in the different reference frames less than the allowable errors. These are just 2 generic types of algorithms, but there are many more for different types of specific uses on larger and smaller spacecrafts.
When compared to other attitude determination sensors, there are a few reasons why star trackers might be advantageous. Before star trackers became as accurate and as advanced as they are today, ray gyros were commonly used in attitude determination algorithms. The problem with these ray gyros, though, is that they can deteriorate, their performance can deteriorate relatively quickly and degrade the performance of the ADCS algorithm that they are in. Star trackers, however, lack the moving parts that these ray gyros have, which allow them to have longer lifespans. Additionally, star trackers allow for Euler angles and quaternions to be directly obtained by comparing the pictures they take to a known star catalog, instead of having to be backed out of an angular measurement, such as with a ray gyro or an IMU. This, in part, allows for star trackers to be as accurate as they are, and they're known to be the most accurate attitude determination sensor there is, with especially at lower angular rates. This also means that star trackers don't require knowledge of any prior information, unlike with IMUs or ray gyros. And the picture here in the bottom right is just an example of how a star tracker might fit into a broader ADCS algorithm. It's sourced from a report from the Hughes company that was working under a NASA contract. And it shows their star tracker called the star's attitude sensor on the bottom of the diagram there, feeding attitude information into the algorithm as a whole, which is going to allow its thrusters and reaction wheels to adjust its attitude to their desired orientation.
So to wrap up this project, we've included 2 slides of references with a various amount of sources from science articles, journals, and of course NASA's website online. Thank you.